This video is over lesson 3, comparing ratios of different types of functions. I went ahead and filled in the vocab for you. Linear functions look like y equals mx plus b. If they're not in that form, as long as the highest power on x is a 1, then it's a linear function. Exponential functions, x is the exponent. An example would be like y equals 3 to the x power. For quadratic functions, the highest power is 2. For example, y equals 3x squared plus 2x plus 1. Let's talk a little bit more about these three types of functions. Here are what we call the parent functions for each one of these graphs. Linear functions, the parent function is f of x equals x, and the graph of that looks like this. A parent function is just the function before it's been transformed or moved around. Quadratic functions, parent functions, is f of x equals x squared, and the exponential functions is f of x equals 2 to the x. Now, I'm going to talk a little bit about what we know about the ratios. One of the things you're expected to be able to do is to tell what kind of function something is just by looking at the graph, an equation, or a table of values from that function. And in order to be able to analyze a table of values, you need to know a little bit about the ratios. So I'm going to pause this video and write down what you need to know, and then I'll unpause, and then you can pause and write down that information. For linear functions, the ratio is that a constant difference in x's result in a constant difference of y's. And here in a moment, I'll show you an example to explain what I mean by that. We will be talking about things called first and second differences. These ratio descriptions all refer to that, which you will find on the next page on example 1. For quadratic functions, we know that if we have a constant difference in x's, it's going to result in a constant second difference of y's. Once again, I'll give you further explanation on that in just a moment. Lastly, we know with exponential functions that there's a constant difference in x's, then that's going to result in a constant product in the difference of y's. Okay, so let's go to example 2 so that you can get more explanation about what we just wrote down. So our graph is linear. And then it says, what methods can you use to verify this type of function selected? So you are looking at the first difference here. So you're looking for a constant first difference. So that's the first thing that I would check. I would just find your first difference every time, because on each one of these methods you're going to be using it. And if it happens to be that it is consistent, then you have a linear function. So let's take a look at this next one and let's see what we think here. Okay, so on this one, the equation says to square each x value. So negative 3 squared is 9, negative 2 squared is 4, negative 1 squared is 1, 0 squared 0, 1 squared 1, 2 squared 4, and 3 squared 9. Okay, so let's go ahead and find that first difference. So between these two, we have a 5, and then a 3, and then a 1, and a 3, and a 5. So this is not constant. So this is not a linear function. So after you have determined that it's not linear, we are going to go ahead and check the second difference. So between 5 and 3, we have a difference of 2. Between 3 and 1, 2. 1 and 1 is 0. 1 and 3, 2. And 3 and 5, 2. So notice that we have a constant second difference here, except for where we see this 0. This is where you're going to have your vertex. So in our original graph, or original table, sorry, this is our vertex. And where our vertex is, it results in a 0 in the second difference. So if you see a 0, but every other number is constant in that second difference, that means your graph is quadratic. So constant second difference. And remember that 1, 0 is okay because that's where your vertex is. Okay. Make sure you've written down how we know and looked at the first and second difference for both of those, and let's go to example 2. All right, so example 2, this time it's asking us to raise our x values, or to basically raise 2 to the x value power. So 2 to the negative 3 power. If you type that in a calculator, you're going to get 1 over 8. 2 to the negative 2 is 1/4. To the negative 1 is 1/2. To the 0 is 1. To the 1 is 2. 2 squared is 4, and 2 cubed is 8. And so to type that in your calculator, you're just doing the 2 caret, and then whatever your number is in parentheses, or depending on what calculator you use, you might not need those parentheses. But that's how I did each one of those to find that number. And then also, if you are using a calculator and you're typing in to find the difference, we're going to do 1/8 minus 1/4, which is 1/8. And 1/4 minus 1/2, which is 1/4. 1/2 minus 1/2, or minus 1 is 1/2. 1 minus 1 is 1, or 1 minus 2, sorry. The difference is, and then we're going up 2, and then we're going up 4. So we kind of see a pattern, but it's not consistent. So it's definitely not linear. So let's go ahead and find our second difference. So between 1/8 and 1/4 is 1/8. 1/4 and 1/2 is 1/4. 1/2 and 1 is 1. 1 and 2 is 1, and 2 and 4 is 2. So once again, we do not see a constant second difference. So this is also not quadratic. So let's go over here and look at our table. It says, what do you notice about the first, or about the differences in this function? Well, they're not constant. And so far we haven't learned what to do there if they're not constant. By what number is the first difference multiplied by to get to the next term in the sequence of y values? So this kind of tells us what we're looking at here. So we're looking at the product that gets us between the first differences. And so between here and here, we multiply by 2, we multiply by 2, we multiply by 2, by 2, and by 2, and these are all multiplications, okay? And so that product is 2. We're multiplying by 2. And when we have a constant product between the first differences, that's when we know that we are looking at an exponential function. So this is going to be an exponential. And then notice it says, how does this value connect to the function? We'll take a look at our function. We had a product of 2, and our function is 2 to the x. So our product is the same as the base. It's interesting. All right, so now we're going to take a look at example 2. We're going to use our skills to see if we know what we're doing here. All right, so remember, the first thing we're looking at is there a pattern in our x's? So on example 2 on this first table, there is a pattern. We're going up by 1. So now we're looking at the first difference. So our first difference, we have 5, 5, 5, and 5. So if all of them are constant on that first difference, write down what you think this type of function is. Pause it if you need some time to think, and then unpause and check your answer. You should get linear. Linear is when our first difference is constant. So in the second one, we're going up by 5, up by 10, up by 20, and up by 40. And then we check our second difference. We have 5, 10, 20. So it's the second difference doesn't make a difference. So now let's look at the product between that first difference. I'm going to get rid of our second. So between 5 and 10, we're multiplying by 2. 10 and 20 multiplying by 2. 20 and 40 multiplying by 2. When that first difference has a constant product between them, remember it is exponential. Okay, and lastly, we have a problem that I changed a little bit from when I originally made the packet, so it may already be fixed in yours, but if it is not, go ahead and cross out that first row and make the last row negative 548. Okay, so we're going to find our first difference. So we have a difference of 4, and then we have a difference of 9, and then another difference of 9, and then a difference of 14. So our first difference is not consistent. Let's go ahead and find our second difference. We have a 5, a 0, and a 5. So remember, as long as our second difference is consistent with the exception of that 1, 0, it is going to be a quadratic function. Go ahead and try your new skills on the independent practice.